On. So we are now recording. Yeah.
Okay, great. So hi everyone. So I'll present this paper and feel free to correct me if I say something incorrect. So this is about block stacking using reinforcement learning with stepwise sparse reward. So I'll go through the motivation and the approach. So the main idea is that block stacking is a difficult problem because the reward function for it is not clear. So if you want to train a robot without any demonstrations, then it's unclear what the feedback should be. And this paper tackles this problem through sparse rewards. So sparse rewards are convenient to design because you don't have to specify how the task should be solved, but rather it is dependent on the outcome of the task. And in this paper, they have different configurations of stacking, like stacking in a tower and stacking in a pyramid. And they have sparse rewards for every step of stacking. So there's nothing new per se in terms of algorithmic novelty, but it introduces in two types of inductive bias. One is through relational structures, so graph neural networks, and the other is through curriculum learning. And using these two ideas of inductive bias, they have an reinforcement learning algorithm, SAC, which solves this task, and it also generalizes well.
Can you explain for people who don't know what's an inductive bias, and for people who know, why is curriculum learning considered an inductive bias?
Oh yes, yeah. Okay. Let me clarify that upfront. So inductive bias is basically you want to impose some kind of structure in your architecture that you know should be good for the particular problem. So through graph neural networks, you say that your neural network architecture is in the form of graphs with different nodes, and you want to learn the relation between different nodes. So the embeddings for the different nodes through feed-forward neural networks. So this is in contrast to having just a single neural network with, say, multiple layers. And curriculum learning is the idea of initially exposing the robot to simpler tasks before moving to gradually complicated tasks. And this is again a form of inductive bias because you are kind of deciding upon a distribution over tasks. So you're not saying that the robot should try to solve the entire task in one go. So you're kind of gradually developing a training scheme where you're exposing it to simpler tasks before more complicated tasks. That is why curriculum learning is also a kind of inductive bias. So if we talk of the state of the art in solving block stacking, it used demonstrations. And this paper does not use any expert demonstration. That is one of the good things. So the problem is challenging because it requires sort of a committed exploration, in the sense that after stacking one block, the robot needs to figure out that it needs to stack another block on top of it and keep doing it sequentially. So this is really an exploration problem as well. So the main related works are, like I mentioned, relational inductive bias. So in this paper, they use graph neural networks. I'll briefly describe graph neural networks after a while. And they use curriculum learning, which I just mentioned. So it's essentially choosing a sampling strategy for training.
Just a quick question. Is curriculum learning the inductive bias?
Yeah, in this paper, they also say so. So in this paper, our contribution, I mean, it is a form of inductive bias. They also say it in the
Curriculum
paper.
learning a prior or something like that. Usually inductive bias is in the model and the data is prior. Am I
Curriculum learning is not a prior because I mean it defines the overall training scheme, right? So
Yes.
you're not saying that you should solve the entire task. You're kind of dividing it. You're imposing an order on the task distribution, which you are imposing. So that is why it's an inductive bias. Does it make sense?
Seems like an
I feel-
optimization strategy rather than a prior.
Exactly. So I feel like it's sort of one of those claims that is exaggerated in the paper, and not. I wouldn't necessarily connect inductive biases with the training scheme.
Yeah.
But
Usually, inductive bias is the way I see this is a very simple mechanism. Any property of the data is a prior. Any property of the model is an inductive bias. And what curriculum does is essentially, let's say, a mechanism of, it's like a property of the algorithm where weights go through a certain path in that sense, right?
Yeah. Yeah.
And in my head, it's still a prior, not an inductive bias. The reason why is the prior is basically you believe these tasks make it work better. That kind of argument.
Yeah,
But
but the idea with a prior is that you will update your prior, right, based on data. But
no, no,
in
no,
this
no. The
case,
prior is anything. Prior is anything that you know going in, right?
I feel like this is not the hill to die on this paper, right?
Okay,
This is
sure. Let's
probably
carry on. Let's carry on.
this is
Yeah.
probably one of those claims that they made to sound good, but the meat of the paper is elsewhere.
yeah, yeah. Okay. So talking of curriculum, there are works that that devise automatic learning of curricula. So how should the task distribution evolve during training? And this paper does not do that. So this paper imposes a particular curricula and different types of curricula, but it is not about learning a better curricula. So yeah, so here's the main contribution of the paper. It combines relational RL and demonstrates that graph-based representations can make use of curriculum for learning this temporally abstracted task. Also, like I mentioned previously, hand designing curriculum or reward functions for this block stacking problem is complicated. So previous methods resorted to demonstrations and imitation learning. This also kind of relates to hierarchical RL in the sense that we'd expect hierarchical RL to be able to solve this kind of tasks. But here they say something that is not particularly true, I guess. Most successful instantiations of hierarchical RL make use of domain knowledge to construct a hierarchy. Yeah, so I'm not sure if most approaches use domain knowledge, like some inherent knowledge in the problem. But yeah, so even hierarchical RL is not able to solve this block stacking task, at least the usual approaches. So let's talk of the, so that is basically description of the related works. And their experimental setup is that, so it's learning from states. So the input to the agent is the end effector positions of the gripper, the current position of all the blocks, and the goal position of the blocks. So the goal position of the block is the final stacked configuration. So these are the inputs to the agent. So is this part clear? Does anyone have any question about what the input is?
Sorry, what is XF?
Here?
The feature representation of the ith block. What does that mean?
So XI is the feature representation of each block is represented. Oh, so so for representing the blocks, you need a position, the orientation.
Mm-hmm.
Do they ever need velocity?
Yeah, they have the 3D Cartesian velocity with respect to the gripper, and also the 3D angular velocity, like this highlighted block here. Oops.
No. But why do they need velocity of the block?
Oh,
Well,
when it's moving,
probably in order to specify the goal condition where you want to say that the velocity should be 0.
No, but the goal is specifically just positions. Next line.
Yeah, but I don't think the block. I mean, the block isn't stacked if the block is moving when it gets to the.
I mean, it's in general the blocks are moving, right? So I think it makes sense. I don't know. I don't know if this feature is used by the policy.
Okay, carry on. Yeah, carry
Yeah.
on.
So yeah, so this is basically so everything is basically given to the agent. And yeah, and so for the episode, the length of every episode is 50 times n steps, where n is the number of blocks. So after that, the episode will terminate. So the agent needs to solve the task within those many steps.
So when they talk about block features, they actually just mean a concatenation of all these of the actual low-level state of the blocks, right? They don't mean a nonlinear dimensionality reduction of that.
No, yeah, nothing learned or nothing reduced, yeah, nothing mapped. So just the raw values, yeah. So all the position, yeah, all those. Okay, so that is the observation space, what the agent observes, and it needs to output an action. Oh, so the action space is 4-dimensional, which is usually the case, consisting of the 3D positions of the end effector and the spacing between the gripper. So that action space is 4-dimensional. So the reward is a stepwise sparse reward, where the robot is rewarded when it places the ith block. And there is a threshold, delta, for specifying when that particular task is solved. So when that particular block has been placed. And yeah, so basically that is the reward function that they design. So it's not a shaped reward. It's not a completely sparse reward either. So a completely sparse reward would be 1 when you have solved the entire stacking problem, and 0 when you have not. But that is too weak a reward signal for learning anything meaningful. So brief about reinforcement learning. So an agent interacts with the environment. You have the environment defined in terms of the state space, the action space. There's a transition function that defines what happens when you take a particular action in a particular state. There's a reward function of the environment, and and a discount factor. So the aim of the agent is to maximize the sum of discounted rewards that it observes. And this is really the optimization objective in reinforcement learning. So if you talk of goal conditioned RL, yeah, so it's an augmented problem where the policies are expressed as not just a function of the current state, but as a function of the current state and the goal state, where you have an explicit goal in mind and your objective is to solve that particular goal. And then the learning problem changes slightly because the reward function and the policy change. They're expressed in terms of the goal, which could be sampled from some goal distribution. So yeah, and the goal distribution may be known or unknown. So in this particular paper, the goal distribution is known because it's the same thing that it needs to solve every time, stack all the blocks one above the other.
So at the same location always?
Not really. No, they don't say it's the same location. Yeah, but I mean the relative goal distribution is at least known, I guess.
But these goals are used in the paper as intermediate goals, so place the next block at this coordinate, that type of thing?
Yes, yeah.
And what about the other goals that are not placed on that are not stacked? So the other blocks that are lying on the ground, are they specified? Is the intermediate goal specified as just leave those blocks that are on the ground as they were?
Oh, no, sorry, no. So the goal is fixed. So the goal is the final configuration. The reward is stepwise sparse. So they don't change. They don't have intermediate goals. Yeah, because that would be kind of difficult. Yeah.
Okay.
Yeah.
That's kind of strange, but yeah.
Yeah, I guess. But okay. So yeah, so then there's graph neural networks where the idea is that you have a graph structure and the nodes are defined by a certain set of features, and the edges between the nodes are neural networks, and the features of each node are updated by message passing, which means that there's some sort of weighted average of the features of the neighboring nodes. So like if we talk of it formally, then there is a vertex set V, and the output that you get after one round of message passing is an updated set of vertices, where the set is defined in terms of the features of each of the vertices. So if the feature representation of the ith vertex at time step t is this, then in every message passing round where each vertex gets updated, you have a query, a key, and a message, which are all independently parameterized functions in the paper. So those are all feed-forward neural networks. And each vertex in the graph receives a message from all the vertices, and its feature representation is updated. So as you can see here, this is the weighted sum of the messages received from all the neighboring nodes. So yeah, so this is basically graph neural network. So I'm not an expert in this. So if anyone has like more questions, I guess we can hold them for later. So the method is extremely simple. So what they do is they have this algorithm called soft actor critic algorithm, and they changed the actor and critic to be graph neural networks, the architecture to just discuss, and that's it basically. So that's it in terms of the policy architecture. So
So
the
wait.
policy. Sorry.
So what's the mapping between the nodes and the physical objects in the world? Is there such a mapping, or
No. So I mean, the graph neural network is not supposed to be like an explicit mapping. Right? So the mappings are all implicit. So it's just the idea that there you can have some relations, but you are not imposing grounding them in the actual environment. But you expect the training procedure to have some meaningful relations such that the task can be solved.
so there's no explicit or implicit grounding, you're saying?
Yeah, no grounding. Yeah. Because yeah, so the various components are so the components meaning the functions that we discussed here for the query, the key, and the message. These are all neural networks, and in this case, they're all these linear layers, 64-dimensional, and they have some residual connection and layer normalization between the output after one round of message passing to go from that output to the next round of message passing.
Does the graph neural network
And
make any assumptions about the nodes being exchangeable or anything like that a typical RL method, a typical MLP representation wouldn't make?
yeah, not sure about that. No, it doesn't make any assumptions, right? So you're saying in some sense it becomes the same as an MLP with like nonlinear.
No, that's not what I'm saying at all. I'm trying to say, if you look at the inputs, so your policy and your value function are going to have some inputs, and I'm trying to say, if you represent this policy and value function as a graph neural network, will that make any extra assumptions that an MLP representation wouldn't make?
No extra assumption apart from the structure and the optimization procedure.
Okay.
So those are the only differences. Does anyone have any comment here? Okay, so they call the architecture RENN, and yeah, so they compare with the baseline. So they have 64. Yeah, whatever. So they compare with their baseline, which has 256 dimensional fully connected layers, which are referred to as MLP.
Before we, sorry to interrupt
Yeah.
again.
Yeah.
Before we move on, is there anyone in the group who has experience or has read papers in relational reinforcement learning?
I have.
Do you wanna comment on how this builds upon that literature, or how is this different?
I don't think it builds on that literature. They're just using a standard graph module as a policy representation. That's it. Like there is nothing else to it.
Okay.
So, in a very simple sense, the graph neural network idea is very generic. You should think of graph neural network not as a separate module, but just as a layer. So you can put a graph layer as you put any sort of MLP layer, and you can do all of the other tricks that you do, like the residual trick or the batch normalization trick, or just like a recurrent model. So you can build in the same way you can build a recurrent model with, let's say, MLP layers. You can do the same with graph layers. So what they have done is, instead of a 2-layer MLP, they probably just use a 2-layer graph network.
So, right. I guess what I'm trying to say is this the first paper that has considered this idea? Or is there a history of such papers and this managed to make it work?
I don't know.
Not
From a perspective of like novelty, I would give it to them that I have not yet. Usually, wherever people use graph networks, there is always this idea of the graph being representing or capturing something specific. Either it's, let's say, a lot of people have used graph for capturing input information in vision. So in these cases, you do object-oriented scene models, right? Or object-oriented dynamics. But I just want to see more. I haven't seen this, but it seems that they haven't done any of that. They just basically say the policy is, well, relational, without specifying what the nodes and what goes in the nodes and what goes in the graph. There has to be something. You still have to decide what are nodes capturing.
Yeah.
Message passing between edges can still happen, but that's fine. My hunch is it's still only capturing the scene representation.
Right.
And yeah.
So Homanga, in their experiments, are the cubes colored in unique ways? So
so
does
does it
each
matter, right? The color, because it's not vision.
Oh, it's only the state, right?
Yeah.
What?
The
How is
paper
the
seems to
input?
be really unclear about the input graph, what the input graph is. It just kind of says there's an input graph that goes in the GNN.
Yeah, my
The
hunch
input
is.
graph.
Yeah, my hunch is what they do is all of the objects, because the objects are provided to you as a list. So if you notice that, go to the previous page. Yeah, observations page. Each block is a representation, right? So the way I would think is every block is a node. Node has a 15-dimensional feature. What they may not do is, or they may or may not do, I don't know. The edges can be, for example, physical connectivity. A on B is an edge. A on ground is an edge. You provide a ground plane, and the robot is in the ground plane, kind of thing. That's the usual way of doing something like this in the past, unless they do something different. What is more interesting is they are able to create an end-to-end policy in general with these kind of systems. Usually for block stacking, multiple block stacking, creating a single end-to-end policy has been an interesting challenge. Of course, the task is fairly straightforward and simple, but just because of the combinatorics of the problem, creating a policy that can handle, let's say, k blocks is usually very hard, and k blocks where the start conditions are randomly sampled is even harder. Usually, random sampling here just means random initial configuration. Each block is independently on the table. So, for example, if I am trying to do the block A on B and B on table, what if I flip the order in the initial condition where it's B on A and A on table? So now you have to grab B, put it on table, and then so on and so forth, kind of thing, right? And those things are much harder to learn. But again, that is not a claim that anybody else has made, so I wouldn't dock any points for this paper for that, anyways. I just want to know what they're actually doing. If it is working, I would argue this is a interesting, neat little trick.
Yeah, rather a combination of tricks, because they have a curriculum that is used to train this. Yes.
Just
So
so
I
you
should
know,
also,
even doing a single pick and place with simple SSE is non-trivial.
yeah. So I should mention that they also use the hindsight experience replay trick, where you relabel states that are previously visited as goals, and also use that learning experience. So when trying to solve a goal from a particular state to another state, you visit intermediate states, and those states can be considered as goals, and you can use the experience from the initial state to your intermediate goals to update your policy. So that is the hindsight experience replay trick, which they use in this paper as well. So yeah, this does. And for curriculum, they consider a bunch of different curriculum. So the direct curriculum is you're learning the entire uh, task. So there is no curriculum essentially. So you need to stack all the 6 blocks starting from scratch. Then the uniform curriculum is the uh, the number of blocks that you will stack in every episode changes uniformly from 1 to 6. So initially you're tasked with stacking just 1 block, sorry, 2 blocks, and then after that you are tasked with stacking 3 blocks, and so on. So you gradually increase the number of blocks that are supposed to be stacked.
Wait, uniformly
Yeah.
sample doesn't mean that, right?
Sorry.
Uniformly sample does not mean that they're increasing it like 1, 2, 3, 4 in that particular order.
But I think they mean to say that only, right? Here, like in this. Okay. Oh, yeah. I see what you mean. So they're not they're not increasing it. They're not necessarily increasing it, but just choosing a particular number.
Yeah.
Okay. Okay. Yeah. Yeah.
Okay. Yeah.
And then they have a sequential method of stacking, where you first pick and place a single block at the goal location. Yeah, and then that block was chosen randomly to be in table or in the airs. And then you need to pick and place 2 blocks, where the goal position of 1 block is sampled on the table, and the goal position for the second block is sampled in this way. And so, and gradually, after you have perfected n-1 blocks, you are tasked to sample n blocks, and this n is sequentially increased from 3 to 6. So this is a sequential curriculum, in the sense that you are sequentially tasked with more difficult stacking problems. And they say that they choose the transition points, like when do you define when you have successfully stacked n-1 blocks to move on to the next stage of the curriculum. They choose it empirically. So yeah. For testing, the results are pretty interesting, in the sense that they evaluate generalization of the policy that has been trained to stack a single tower on 3 different types of conditions: stacking a single tower in the test time, stacking multiple towers, and stacking a pyramid. So if I quickly move to the appendix. So these are the pyramid configurations that they have. So they did not train for these. they just evaluated where the final goal configuration is this, and it seems to be able to stack into this pyramid configuration as well. So in training, it's only vertically stacking all on top of one another. Similarly, they evaluated on stacking.
How is the reward function set specified such that is the reward function globally specified or is the reward function locally specified? So when I say locally specified,
Yeah, so let me go back to the reward function. So this is the reward function here. So they have one term that defines whether a particular block has been stacked in the goal location, in the sense that the distance between the goal location and that particular block's location is less than delta. And they have another term in the reward function to encourage the gripper to move away after stacking it. Otherwise, they observe that the gripper brings it to that location and remains there.
so what I see is there is a step reward per block. So they define the order. The ordering is defined, right? Because the ordering is implicitly defined by the reward model. So if they want A on B, B on C, then the reward model will have B first and then A first, A after, right? And so the solution is given to them, at least they have solved, or they basically don't worry about the ordering ever, right? So the policy never has to decide which block to pick at this point, or
I mean,
high
it does
level
not
ordering.
have to decide. Because this is
that's
decided by
given to
reward
you.
function.
Yeah. Okay. Okay, that's good.
Yeah. Does anyone have any questions?
Where do you see that in the reward that the order is given? Isn't it always taking a sum over all the blocks?
No. Look at this, right? The first line is we use a stepwise reward function where only when it places the ith reward from its desired goal location. So now basically this I is essentially a list of blocks, and so this is the part where I want to be very clear, right? Is it the sum over all the blocks?
Sorry, what is the sum over all the blocks?
So the ordering, I think Dylan pointed out correctly, both me and Homanga were wrong actually. If you look at the last line, the overall reward, it is just a sum over all blocks. So there is no, so the policy does have to decide.
But the goal location.
So all of the goal locations are simultaneously specified, rather than in an order.
Yeah, because you know them, right?
Yeah. So all of the goal locations are simultaneously specified.
Yes.
And this is precisely where having a graph structured implicit representation really comes into place, or at least like this is where a graph module would really be useful.
But the goal locations are specified, but it doesn't matter which block you bring to that goal location. All the blocks are identical.
No, I think the ith block, because the ordering of block I is defined by the ordering in the state representation.
Okay.
Does it say that? That the blocks are interchangeable?
Yeah, I'm confused now.
I would assume that the graph module allows them to be interchangeable unless they specify it. My understanding is they do.
Okay.
But this doesn't change anything, by the way. So if you don't have block IDs and the blocks are interchangeable, then it makes the problem easier rather than harder.
Yeah, that is what I assumed. That is the case. I mean, in my understanding.
But then doing that loss is actually harder, because how do you know which loss to do which? Like you have n-way loss in that sense. So usually you have every like block ID X needs to go to a goal ID X. Right? So you have a list of blocks and a list of goals, and it's one-to-one matching.
Yeah. Okay. Does anyone have any comment here?
I mean, not for the particular thing, but I have a comment about the use of GNNs both for the I can see why one would use it for the policy. It's sort of I need to understand more why one would use it for the value function as well. And I think the question that I have at the moment is, does introducing GNN as the architecture mean that inherently you're putting some constraint on the value function to be somewhat low rank? No.
This is just a state representation. So either you can explicitly make the state a graph and then operate, so you can do a graph-to-graph module kind of thing. Instead, they basically input the state into this graph, and everything else is a graph module. So essentially, they are arguing the state is a graph, which is true in this case. Would you agree that the state is a simple graph? And if you can represent the state as a graph, then all of the further computation is essentially an MLP on top of this graph representation.
So there is an MLP on top of this.
There is an MLP always. Even within the graph module, right? When you do message passing and all of this kind of stuff, they are essentially small MLPs.
Oh, so the edges are MLPs in general, but in their case, they have linear layers. Yeah.
So but in general, there is always a layer. So when you do this thing, I think the easiest way to explain this is, I can try to go over graph neural networks next time rather than getting into the detail.
I think my question is, does the fact that you're putting graph neural networks as the architecture and then having an MLP, does that inherently help make the value function low rank?
I don't know if it is low rank. It's basically that because the input data is graph structured, right? Or input data is better represented as a graph. Hence, basically it's like this, that it's the convolutional layer argument. When I'm doing classification, the initial featureizer or the encoder is a convolutional layer, and then I put an MLP to make decisions. It's the same argument that the input data is graph structured. Hence, you put the structure in the model. That's it. So I don't think it's the low rank argument. Perhaps it's the separability argument that value function estimation actually works in this representation space rather than let's say a purely just MLP space where you can put all of the list of these objects into an MLP and then go from there. So in that sense, it's actually reasonably neat.
They don't discuss any of those though. Just the high level intuition of
because these things are like too from a machine learning perspective. There's like nothing in here.
Yeah.
Right. It's actually surprising that works, and that is why I think Richard, who was the first author, is like second year or third year student. Is just like from a perspective of like it required a lot of execution effort, but little algorithmic effort.
Just a small thing. I tried pulling up some of the code, and I'm having trouble figuring it out, just to figure out what the input vertices to the graph neural network really are. But at a glance, it does look like there's one vertex per block. I'm not sure. So I think that there could be some grounding.
The input is this is the input.
No. It's not the input. He was asking like, how is this fed into the graph? Because the graph still needs to be initialized in like at the input time, right? Even in a graph neural network, right? You have to specify at least three things: vertices, their adjacency matrix, so that you have edges or connectivity structure, and any sort of attributes or weights on top of edges and vertices. So this is what I was saying, right? That they would have one vertex per block. Every block will have a 15-dimensional feature vector. And then I don't know what explicitly edges mean here, but most likely I would just assume edges are like on top kind of argument, right? Or vicinity maybe. Like Euclidean distance could also be something that you could do, right? Or vertical. I don't know what exactly did they do, but from my experience, we have tried this. It's non-trivial to define edges there because it's simple ideas don't work. So looking into code would be useful here. But again,
because they don't have a lot of details in the paper.
Yeah, I think I would prefer to like see more if there is anything else before jumping into sort of getting into these details.
To Florian's point, I think I was at a Fields talk where the presenter was showing how I think LSTMs with a certain block sparsity structure in the weights is reduced to certain graph neural networks.
Yeah.
Yeah, I think the reason why I'm asking was that there was a recent paper which I posted on the reading group at iClear, which was showing that for many of the Mujoko tasks, or many of the Atari tasks as well, if you look at the state action value function, almost always it has low rank structure. So if GNNs manage to just capture that low rank structure, then that's great. But I think what Kevin is saying is exactly the type of connection that would be interesting, I think.
Yeah. Okay. Yeah. So like going over the results, like I mentioned, they train it for stacking a vertical block sequence, and they evaluate zero shot. So they train it completely and they don't fine tune it on different evaluation setups. So the first is the same setup as training, where there's just a single tower of all the blocks. And the second setup is multiple towers, so no fine tuning again. And then the third final is pyramid evaluation. So yeah, so that's kind of interesting. That is able to solve all these three configurations without having been trained on them at all. And they also show some emergent strategies that evolve because of using this sparse reward. So when you're not using a dense reward, you're not guiding the policy explicitly. So some interesting behaviors emerge, like you need to push blocks to grasp another block and so on. They're necessary for solving the task. So there's the first work that reports such zero-shot generalization on the block stacking using RL. Yeah, that's pretty much it, I guess.
Can we talk about comparisons? Did they what
Yeah,
baselines they compared with?
So the main comparison is here. So they say that there is the approach is sample efficient, in the sense that if you look at the graph, the green curve is all of them are their approaches, the baselines, and the green curve is the architecture, the graph neural network in the actor and critic, along with the sequential curriculum strategy, and it has an increase here. You can see.
Yeah,
also,
but from this figure,
yes.
Can we understand which was the factor that contributed the most? Like, have they tried variations where they use the GNN layers only on the policy and not on the value
GNN
function?
layers? No, not that. So in all the cases, they have GNNs on both the policy and the value function.
Mm-hmm.
In the other case, they have just MLP instead of GNNs.
Mm-hmm.
So
but
those
also,
are the two variations.
But also the curriculum learning setup also really helps them. I mean, look at the red curve versus the green curve.
Definitely, yeah.
So, I mean, is the argument that the combination helped them, or was it one that helped them more than others?
So if you look at the red curve, this direct,
mm-hmm.
and I don't know how to compare it. So this direct and this sequential will give you the difference between using the curriculum, not using it, and this direct and MLP sequential and this sequential will give you the difference between the graph structure. So
can you remind us what's the difference between uniform and sequential in the learning?
Yeah, so as Mayank
training
pointed out,
strategies?
in uniform, you just randomly choose the number of blocks to be stacked in a particular episode. So it does not gradually increase. So it's not essentially a curriculum technically. So yeah, you just uniformly choose how many blocks you'll stack in each episode. Yeah. So yeah, basically.
I think a very useful thing here is figure 4. I think that's the biggest takeaway according to me. Everything else is the less useful.
Yes. Oh, yeah.
this is the most, because this is the internal representation evolving over time. 1 through 6 are blocks, and this is exactly what I was saying. Blocks are ID'd if you look at. So like ID 1 is green, yellow, blue, pink, red, and black. This the way to read this matrix is first look for a block that you're looking on x-axis, and then that block is resting on the block on y-axis. So ith block on x-axis, jth block on y-axis, kind of thing, right? So the first step would be block number 2. The model believes block number 2 rests on block 2, 3, or 4, right? So block number 2 is yellow, and the block sort of 2, 3, 4 are yellow, blue, and pink, right? So either it's yellow on yellow, yellow on blue, yellow and pink kind of thing. So this representation is a more useful way of thinking about this. And what is interesting is, of course, I don't have time right now to get into this. Maybe this is the representation of the future, not necessarily like what is needed rather than what is happening now. Or you can encode all sorts of things in this representation, right? So I can represent the scene in this simple 6x6 matrix. I can represent what is wanted, like the gradient of this matrix, because this is what state representation becomes. So now you can design value functions in this space or whatever you want, right? So this 6x6 matrix of scalars becomes your state representation, and then you can do whatever you want, whether from the policy perspective or from the value perspective. Or prediction perspective or anything, right? So this is the state representation that graph outputs. And the gradient of this representation has a very clear meaning. So you can do everything in this space. Like you can do graph dynamics. We have done this graph to graph dynamics. You can do value learning or whatever. And that is why you need value function also to have the same structure as policy. Okay. I have to go now, but Florian is also a host, so the meeting will not end. Okay.
So actually, I think we need to go as well because we have another another meeting. So maybe you can unless Homanga has
no.
no, this is good.